Hello everyone, this is Orekoya Olusegun Physics Mathematics Fundamental on YouTube. Please, before we go into today's topic, do not forget to like, share, subscribe, and click on the notification button to have more of my video. Today, we are going to introduce ourselves to the fundamental concepts of calculus. So we are going to take a line of study on the application of calculus, and this is integration. So application of integration. Integration also means antiderivative, and what I want us to also remember is to go back to my other video where I discuss the other aspect of calculus, which is differentiation. Differentiation can also be referred to as instantaneous slope of a particular function. So today, like I've said, we are going to dwell on application of integration, and then we use it in determination of the area under curve as well as the volume of a revolution given a particular curve of a function. Thank you. Now, let's consider the arbitrary graph of this function y is equal to f of x at intersecting the horizontal axis. This particular axis is for the independent variable, while the vertical axis is for the dependent variable. Let's say the graph of this y is equal to f of x is this particular graph that I've drawn here. Let's take arbitrary points here, call it point P1. Let me take another point here, call it point P2. Now, to locate this point P1, we go from the origin here to this place along the x-axis. Let's say the distance covered is x. Now, to get to this particular point along the horizontal axis, we move from the origin down to this place, and we are covering this particular unit of distance, and therefore these points on the x-axis will be x plus delta x, x plus delta x. So in a nutshell, I can think about this particular limit under the curve, and I want to take this particular area under this curve. Don't forget that this particular point that I have here is x and y, because when I trace this along the y-axis, this place will be y. When I trace this point along the y-axis, the distance between y and this particular place is delta y. So that means from the origin to this point on the y-axis, the value of the y here will be y plus delta y. Take note of that. Now, if you look very well concerning this shape, I want to bring it out. This particular shape here, I want to bring it out. I will have something that looks like this. And the base for this particular area under the curve, this particular shape, the base of that shape is very obvious. That is delta x. And this particular side of the shape from here to here, like I said, is y plus delta y. So this place is y plus delta y. Now this side of this particular shape that I have here, this particular side from here to here is y. So I have y. So this area, I put it as delta a. If you look at this shape very well, this shape almost resembles a trapezium, like this, such that this place will be the A and this place will be the B of your trapezium, and the distance between them here is h. And we know that for this area of this trapezium, I'm talking about trapezium in geometry, we know that the area A of this trapezium, this particular region, being covered by this boundary, the area is given as half A plus B H. Now, we can use it to also get approximate area of this shape, this particular area. So, this delta A that I have here is written as half. Our A here corresponds to this Y plus, then our B here corresponds to Y plus delta Y, Y plus delta Y. Then the distance between these parallel lines on this trapezium, the distance H corresponds to delta X here. Now, if you look at this particular expression that I have here, we can simplify it as 1 over 2 brackets 2y plus delta y then times delta x. If you use this half to multiply this bracket, the 2 will cancel 2 here. So I'm going to have y plus delta y divided by 2, everything times this delta x. So that will be the area, delta A, under this curve. We can see here. So I want to write this one here for us to see better. So what I have here now, I can rewrite it as delta A is equal to y plus delta y divided by 2 times delta x. According to calculus, as delta x tends to 0, delta y2 will be tending to 0. In this case now, when delta x tends to 0 and delta y tends to 0, the quantity that will be here will be approximately equal to 0. And then during these limits that we have here, I can write it as limits of this area. It's same thing as limits of this expression I have here, as delta x tends to 0, delta y tends to 0. So the limit of this area in calculus is the A. And the limits that I have here, delta x will be the x. And this one has turned to 0 because delta x tends to 0. So I have y dx. Now, integration of both sides now with respect to x is same as integral y dx. When you are integrating this infinitesimally small quantity, it will be added to the full quantity, which is the total area under this curve, and which is given as integral y dx. So this is the formula for area under graph in calculus. Now, for instance, you are given a problem that find the area under the curve y is equal to 3s squared in the interval x in interval 1, 4 on x axis. So if you look at this problem now, let's say the graph, arbitrary graph for this is not, the graph is not drawn to scale. Let's say the arbitrary graph that I'm having for this particular problem is here, and the limit on the x-axis as given to us is 1 to 4 here. So we are asked to calculate this area under this curve. According to this formula that I have here, the area under that curve can be given, the area can be given as integral y dx, and our limits from a to b. So the limits that I have here is the limits of this particular interval, which is 1 to 4. So I can have integral 1 to 4 of y. Our y that we have here is 3s squared. So you write 3s squared dx. So in my other video, I've discussed how to integrate a given function. So you are advised to go back to my other video. So this one now that I have here, the a will now be, I will put the interval outside here like this, 1 to 4. So you add 1 to this power. So you have 3x raised to the power 2 plus 1. Whatever that you have here, divide it. Use it to divide whatever we have here. That is 2 plus 1. So I have the area now. You know, this become 3x raised to the power 3 divided by 3 within the limit 1 to 4. So the area now, here, these 3 cancel these 3. So I have x raised to the power 3 in the limit 1 to 4. The meaning of this limit is that we substitute the first limit here, then we subtract the second limit. So I'm going to have a is equal to 4 raised to the power 3. Take away, you put 1 here, 1 raised to the power 3. And we know that 4 times 4, 16. 16 times 4, that's 64. So 4 raised to the power 3 is 64. 1 raised to the power 3 is 1. So our answer here is 63 units, you see units squared. So this is how to find area under curve. Now the next one we are going to take is how to find the volume of revolution generated by an arbitrary function. So we meet in my next video to discuss on how to determine volume of revolution using integration in calculus. Thank you for having my time. Have a nice day.